Next, NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again after months of spouting gibberish.
Voyager 2 left Earth over 4 decades ago, carrying instruments that still dazzle scientists today. But the latest discovery holds something too bizarre to ignore. An AI-developed tool might have found a hidden message encoded in the images from this legendary spacecraft. Early results have stunned experts worldwide, kicking off a wave of speculation and excitement. Is there truly something beyond the fuzzy pixels of Voyager 2's cosmic snapshots, or is this just a data glitch? The launch and early aims of Voyager 2. Voyager 2 lifted off from Cape Canaveral on August 20th, 1977, aboard a Titan II rocket. It was one half of NASA's daring Grand Tour program, the other half being Voyager 1, which would follow a slightly different path. The Grand Tour concept had emerged during the 1960s, when mission planners noticed that a rare alignment of Jupiter, Saturn, Uranus, and Neptune would take place in the late 1970s. This alignment would allow a suitably equipped spacecraft to capitalize on gravity assists at several giant planets, thereby visiting multiple targets in one trip. Since such an alignment would not repeat for another 175 years, NASA seized the opportunity. Voyager 2 was outfitted with various instruments designed to reveal data about planetary systems and the transitions between them. Among these instruments were a plasma detector, a plasma wave subsystem, a cosmic ray sensor, a magnetometer, an imaging science subsystem consisting of narrow and wide-angle cameras, and additional support gear for navigation and data collection. The original plan was that Voyager 2 would visit Jupiter and Saturn, with a possible extension if the spacecraft remained healthy. In practice, the craft went on to explore Uranus and Neptune, something not envisioned as a certainty in the earliest mission outlines. Since reliability was critical, every system was built with enough redundancy and robust engineering to withstand the extremes of deep space. Engineers also included the now famous Golden Record, a gold-plated copper disc containing earthly sounds, images, and multilingual greetings. While primarily symbolic, the record showcased the mission's broader goal to share humanity's story with whichever intelligence might intercept the probe one day. The spacecraft was powered by radioisotope thermoelectric generators, RTGs, that converted heat from decaying plutonium-238 into electricity. This power source, though stable, would diminish slowly over many years, forcing careful resource management. Voyager 2's early months tested its systems, calibrating instruments, and confirming that the spacecraft could navigate the harsh environment between Earth and Jupiter. By 1978, mission teams felt confident enough in Voyager 2's performance that they began preparing for the Jupiter encounter. It was here that the craft would demonstrate its camera systems, capturing images of the planet's swirling atmosphere and its many intriguing moons. Beyond Jupiter lay Saturn, and if everything went as hoped, the craft would then press on to the lesser-known worlds of Uranus and Neptune. The Grand Tour of the Outer Planets. During its approach to Jupiter in 1979, Voyager 2 recorded spectacular images that showcased Jupiter's multicolored cloud bands and the iconic Great Red Spot. The plasma instruments measured Jovian space weather, and the magnetometer investigated Jupiter's large magnetic field, which extends millions of kilometers into space. Observations of Io, Europa, Ganymede, and Callisto revealed intense geological and possibly subsurface processes. In particular, scientists were stunned to see active volcanism on Io, the first time eruptions had been observed beyond Earth. With Jupiter behind it, Voyager 2 used the gravitational nudge from that planet to speed onward to Saturn, arriving in 1981. Its cameras detected braided rings, subtle ring divisions, and mysterious features called spokes within the rings. The magnetometer traced the shape of Saturn's magnetosphere and provided data on how the planet's environment interacts with the supersonic solar wind. Saturn's moons, including Titan, Rhea, and others were examined for geological features. Though Voyager 1 had already visited Saturn, Voyager 2's instruments added coverage and offered a second look at regions missed by the first craft. The real uniqueness of Voyager 2's journey came next. The encounters with Uranus, 1986, and Neptune, 1989. Uranus, a planet with a large axial tilt, brought surprises such as a strangely oriented magnetic field and new rings that were faint but detectable. Voyager 2 discovered multiple new moons, each with its own characteristics. The magnetometer found that Uranus's magnetosphere was tilted relative to its rotation axis, adding complexity to the models of how giant planet magnetic fields work. Neptune proved equally fascinating, with Voyager 2 capturing images of the Great Dark Spot, which resembled a storm akin to Jupiter's, but was short-lived in comparison. The spacecraft found faint rings around Neptune and made groundbreaking observations of the moon Triton, where geysers spouted material despite the extreme cold. Having completed this unprecedented route, Voyager 2 had transformed textbooks on planetary astronomy. It had shown that gas giants were varied, magnetically active, and orbited by dynamic satellites. By 1989, many described Voyager 2 as the single most productive planetary mission yet launched. Moving beyond the known solar system. After the Neptune encounter, flight controllers directed Voyager 2 farther into the outer solar system. At that point, NASA effectively ended its primary mission, switching focus to an extended mission that sought to explore the heliosphere's outer boundaries. The cameras, which had taken iconic pictures, were placed in standby or low-power modes, reinforcing the ship's ability to supply energy to its plasma, cosmic ray, and magnetic instruments. The logic was straightforward. Once past Neptune, there were no more big planets to image, and the available power would be better spent collecting data on the environment that shapes the fringes of our star system. Operators dealt with decreasing power from the RTGs. Each year, the spacecraft had a bit less electricity to run its instruments, prompting them to shut down heaters and non-essential components. Meanwhile, through these cutbacks, the spacecraft continued beaming back a wealth of data on charged particles, magnetic fields, and plasma waves. The cosmic ray detectors observed how interstellar radiation filtered into the regions still touched by the sun's wind. The magnetometer measured subtle shifts in the solar magnetic field, which extends outward from the sun. Around the turn of the century, scientists increasingly examined how Voyager 2's data lined up with that of its twin, Voyager 1, which had departed the plane of the ecliptic in a different direction. The partnership of these probes offered a near 360-degree perspective on how solar wind flows outward and merges with interstellar currents. By analyzing these readings over time, researchers fine-tuned theories about how the heliosphere is shaped, whether it is spherical, comet-like, or subject to external pressure from the galaxy. The spacecraft tracked solar eruptions that traversed billions of kilometers, enabling observers to study how fast they traveled and how they weakened over distance. As it made its way outward, Voyager 2 was nearing the milestone of the termination shock, where the solar wind slows from supersonic to subsonic speeds. Scientists wanted to see how the local magnetic field might behave and how cosmic rays might bypass the diminishing solar wind. Such observations had relevance for space weather modeling and cosmic radiation predictions. The data was slow in coming, as transmissions took many hours to travel Earthward, but the trickle of information was steady enough to construct a broader picture of what awaits in the interstellar domain. Crossing into interstellar space. In November 2018, Voyager 2 crossed the heliopause, becoming the second human-made object to enter interstellar space after Voyager 1's earlier crossing in 2012. Teams back on Earth identified the crossing point by watching for abrupt changes in plasma density, magnetic field direction, and cosmic ray intensity. Inside the heliosphere, solar wind particles dominate, pushing outward. Beyond the heliopause, the densities of high-energy cosmic rays rose, and the local magnetic field no longer aligned with that emanating from the Sun. These sets of indicators converged around the same time, confirming Voyager 2's exit from the solar bubble. This step was monumental for astrophysics because it afforded a second vantage on how the Sun's influence meets the galaxy at large. Comparing Voyager 1 and Voyager 2 datasets showed that the heliosphere can differ significantly at different points along its boundary. Some areas might be more compressed, possibly due to external pressure or changes in interstellar conditions. For instance, Voyager 2 detected certain magnetic fluctuations that were higher than expected, suggesting that the region where our Sun's outward flow stops might shift or pulsate over time. Although the spacecraft was now in interstellar space, it still had enough energy left in its RTGs to run a minimal suite of instruments, particularly the cosmic ray subsystem, the magnetometer, plasma detectors, and occasionally the plasma wave subsystem. Engineers continued to face the challenge of power distribution, shutting off heaters or rotating instrument usage. Communication delays exceeded 16 hours one way, calling for thorough planning whenever commands were sent or software updates were uploaded. By this time, the cameras had been silent for decades, as they were seen as both burdensome in terms of power and unlikely to produce meaningful images in the darkness beyond Neptune. The challenge of capturing images at extreme distances. Taking pictures in the outermost stretches of the solar system and beyond is not straightforward. Although Voyager 2's cameras once operated effectively at Jupiter, Saturn, Uranus, and Neptune, those environments featured bright planets reflecting solar light. By the time the spacecraft moved outside Neptune's orbit, solar illumination dropped to a fraction of what it is near Earth. The cameras themselves, built in the 1970s, were not designed for ultra-low-light astrophotography. Even for short exposures near Neptune, some creativity was needed to reduce motion blur and cosmic ray interference. In interstellar space, the situation is even more difficult. The spacecraft's design allocated only certain wattages to each system, and each watt matters. Over the years, the RTGs lost power. If the cameras were reactivated, that would mean other instruments might need to power down, or heaters could be switched off. Mechanical issues were another question. The camera shutters, filter wheels, and stepping motors had long been dormant. If these parts jammed, it could cause unforeseen problems, possibly interrupting data storage routines or damaging electronics that still had to function for other observations. Another factor was cosmic rays, which become more common as the spacecraft moves away from the protective influence of the Sun's magnetic field. These high-energy particles can cause bright spots and streaks on images, particularly during long exposures. Without advanced shielding or error correction, an older camera might record frames dominated by random speckles. Each cosmic ray hit appears like a flare in a single pixel or cluster of pixels, complicating the already faint signals that might come from the background. Any image captured at these distances would need extended exposure time, several hours or more, to accumulate enough photons to stand out from the sensor's noise floor. Each additional minute of exposure invites more cosmic ray strikes. Even with multiple frames that could be stacked, the resulting raw images might look like near-random static. By the early 2000s and 20s, new data processing methods, particularly machine learning and quantum-assisted denoising, began to offer a chance to extract real signals from heavily corrupted images. This technological shift prompted some engineers to propose reviving Voyager 2's cameras to attempt a final look at the heliopause. Reviving the cameras for a final attempt. In 2024, a small team at NASA's Jet Propulsion Laboratory started to work out a plan to reactivate Voyager 2's imaging science subsystem, focusing on capturing potential emissions or light patterns at the heliopause. Their argument was that the vacuum of interstellar space might not be completely dark if plasma or dust processes emit faint glows. If the camera and tape recorder functioned well enough, and if the spacecraft's orientation could be managed carefully, a handful of ultra-long exposures might catch a fleeting glimpse of boundary structures. A major barrier to this plan was power allocation. The spacecraft's total power output was at an all-time low, so any camera operation demanded turning off or reducing certain other devices. Sometimes that meant partial shutdown of heaters or science instruments for hours at a stretch. Another issue was the mechanical risk of moving the filter wheels and shutters for the first time in decades. Engineers tested each movement carefully, issuing low-level commands to rotate a filter wheel by a fraction, then waiting for telemetry to confirm success. They warmed the mechanisms to ensure lubricants were not too viscous. This slow, methodical approach took months, as each step required a round-trip communication time of over 32 hours. Software also needed to be updated. Code from the 1970s had to be merged with more modern data compression routines. Even though the spacecraft's main computers are simple by contemporary standards, flight engineers carefully integrated blocks of new instructions to handle the camera exposures, ensuring that any error routines or watchdog timers would not shut down the entire probe. Tests showed that the cameras could still generate valid frame data, though the images were expected to be extremely noisy. With these preparations in place, NASA approved a short imaging campaign, believing the potential insights about the heliopause might justify the costs and risks. In March 2025, the new commands were uplinked. The camera systems powered on, filter wheels turned, and shutters opened for exposures lasting 2 to 4 hours each. The spacecraft needed to remain stable, so other instruments were placed on minimal usage to free up the necessary watts. Each raw exposure was saved to tape and then played back to Earth at very low bit rates over several days. Mission members recognized the data might look like almost pure noise, but believed advanced processing might salvage hidden signals. Data analysis and emerging clue. When the first raw frames arrived on Earth in April 2025, they appeared mostly as static. Bright points from cosmic rays dotted the black background, with occasional streaks. Nonetheless, scientists cross-checked each image against time-stamped logs from the cosmic ray subsystem, plasma wave data, and magnetometer readings. They stacked the exposures, aligning them based on approximate star positions when any star was visible, and the spacecraft's known orientation during each multi-hour capture. The idea was that real patterns would show up consistently, while random noise would vary from frame to frame. NASA used a deep learning denoising model adapted from Cassini ring imagery. This model had been trained to distinguish faint ring or dust signatures from the random backgrounds typical in that environment. Meanwhile, the European Space Agency applied a quantum-assisted filtering pipeline pioneered during the analysis of extremely dim signals from comet studies. Initially, each team worked independently to avoid bias. Then they compared notes, discovering that both pipelines revealed consistent filament-like structures running across large parts of the stacked images. These filaments were not bright or crisp, but they repeated in separate exposures on overlapping time intervals. Technical groups posited that these filamentary streaks might correlate with spikes in plasma wave or cosmic ray data. For instance, if the cosmic ray instrument observed a brief rise in high-energy particles, the denoised images sometimes showed a slight enhancement in specific filaments. It was as if lumps of charged particles lit up invisible lines or tubes for short spans. To bolster this interpretation, researchers matched the brightness in each pixel cluster to the recorded flux of energetic particle. The correlation was not perfect, but was strong enough to rule out random chance. Some frames included geometric oddities, reminiscent of lattices or faint hexagonal cells. Experts argued about whether these shapes could be caused by the camera's spin synchronization. However, the spin axis alignment tests did not confirm a simple mechanical explanation. Others suggested that certain plasma instabilities might manifest as cell-like patterns. The general reaction was curiosity mixed with caution, as so little had been documented visually at the heliopause. NASA's partial announcement in mid-2025 confirmed that preliminary data hinted at large-scale structures, though the agency did not commit to any single theory about what they signified. Potential explanations for visible filaments. As the debate expanded, scientists grouped the possible origins of the filaments into a few main categories. One widely discussed approach was that the lines visible in the stacked frames were magnetic filaments. The sun's magnetic field, stretching outward in the solar wind, may entangle with the local interstellar field, creating zones of twisted field lines. Charged particles traveling along these lines could emit or scatter a low level of light, especially if accelerated by reconnection events that convert magnetic energy into particle motion. A second possibility invoked dust emissions. Interstellar speed dust grains crossing from outside might accumulate near the heliopause, charging up due to collisions with solar wind or cosmic rays. As the dust charges, it could luminesce faintly. If dust grains cluster in strands or sheets, a long exposure might reveal these filaments. Material carried by solar wind flows could also bunch up at the boundary, giving them enough density to become marginally visible under careful denoising. A third explanation centered on plasma waves and resonances. Plasma physicists noted that wave instabilities at the boundary could produce localized sheets of higher particle density, which might glow or reflect just a trickle of sunlight. The wave patterns might look filamentary if certain modes propagate across the boundary. Alternatively, standing waves or resonant cavities in the heliosheath might form repeating lines or arcs. The correlation with cosmic ray flux spikes supports this notion, since wave activity can channel energetic particles in discrete pathways. More speculative individuals pointed to exotic physics, suggesting that axion-like dark matter might transform into photons near strong magnetic fields. This phenomenon, though unproven, has been floated by some researchers trying to explain cosmic ray anomalies. If dark matter existed in sufficient density around the heliopause and experienced field interactions, it could yield faint streams of light. Many mainstream scientists viewed this as a long shot, but they admitted it was not impossible in principle. Regardless of which core process dominated, nearly everyone agreed that the repeated filament phenomena were intriguing enough to warrant deeper analysis. Each proposed explanation matched some features of the data but left gaps. For instance, while dust glow can account for certain brightness fluctuations, magnetic filaments better explain timing correlation. Plasma waves could produce a variety of patterns, but that might not clarify the geometric shapes. Axion-like particles remain too speculative for most. This variety of interpretations revealed how little is definitively known about the heliosphere's outer boundary. Hexagons, spokes, and other puzzling patterns. Beyond the filaments, NASA and ESA both noticed patterns akin to hexagonal lattices or spokes. Some frames displayed lines crossing at 60-degree angle, forming a structure reminiscent of a cosmic wheel with 12 spokes. Plasma wave experts found it interesting that the measured wave frequencies on Voyager 2 had a quasi-periodic behavior, which might produce stable or repeated geometries over large spatial scales. If wave resonances exist, they might drive matter or charged particles into coherent patterns, not unlike the shapes that appear in fluid systems under certain oscillations. Others at NASA hypothesized that the hexagons or spokes might be illusions from partial sensor readouts. They tested for shutter timing offsets, spin axis alignments, or lens reflections, but repeated confirmations from separate algorithms, one from NASA, one from ESA, made it less likely these were purely mechanical artifacts. The magnetometer readings gave no straightforward reason for a hexagon. Some invoked the well-known hexagon on Saturn's North Pole as a cautionary example. Nature can sometimes produce geometric patterns under rotating fluid or gas conditions. Perhaps the heliopause similarly supports a phenomenon that self-organizes into stable shapes. Another interesting angle is that the cosmic ray flux and plasma wave data Both rose in short bursts timed with the spoke appearances. That hints at a factor that periodically channels energetic particles in radial line. If the boundary region behaves like a bell that rings in discrete modes, certain arcs or spokes might reflect density waves. The hexagons, if real, could mark boundary zones where wavefronts meet. Meanwhile, dust-based explanations might still hold if the dust is sorted into compartments by wave activity, forming a honeycomb-like pattern. In a mid-2025 briefing, NASA stated that it would be premature to declare the presence of stable hexagonal cells or radial spokes as definitive. However, the repeated manifestations across multiple frames and different times made random chance unlikely. NASA and ESA continued analyzing the data, releasing partial results in peer-reviewed journals that described potential plasma or dust interactions. Researchers from universities worldwide joined the discussion, applying further denoising algorithms or alternative image enhancement strategies. No single group reached a final conclusion, evidence that the puzzle is more intricate than a single phenomenon. The wider context and long-term research outlook, all of these findings place Voyager 2 at the heart of a new phase in heliospheric research. Even though it is an aging spacecraft with limited wattage, it has delivered an unexpected visual snapshot of a domain once deemed invisible to standard cameras. The significance extends beyond merely capturing pretty pictures. Each faint line or shape is potentially a clue to the interplay between solar plasma and interstellar matter. Studying how magnetized plasma organizes itself at the boundary helps scientists anticipate cosmic ray patterns, analyze the system's shape, and explore how the sun's influence eventually gives way to galactic conditions. The data also deepen cross-mission collaborations. Voyager 2's newly processed frames can be compared with in-situ measurements from New Horizons in the Kuiper Belt or with observations from Earth-based radio telescopes. Although none of these vantage points can replicate the direct contact that Voyager 2 has with that region, the correlation of multiple data streams can reduce ambiguities. ESA and NASA together have a history of turning seemingly unusable data into discoveries, like Cassini's ring science or Rosetta's comet studies, and now apply those lessons to a 1970s-era probe well past its original scope. Engineers remain cautious about scheduling more camera exposures. Each additional attempt to gather data takes precious power away from other instruments, and the camera motors could seize or fail outright during mechanical operations. If the new exposures showed changes in the spoke arrangement or the filament angles, that would confirm that the boundary region is dynamic and evolves over short timescales. If no changes appeared, it might mean the pattern is more stable, raising different questions about how or why it persists. Either way, each day that Voyager 2 stays alive is an opportunity to refine understanding of how star systems interface with the broader galaxy. Even from a cosmic perspective, these hints of structure at the heliopause echo broader astrophysical questions. Every star, presumably, has a boundary zone where its wind encounters the interstellar medium. If filaments, hexagons, or spokes can form around the Sun, they could appear around other stars as well. Observers have noted bow shocks around certain stars moving rapidly through dense gas, or around regions of star formation. If an advanced civilization launched a probe to one of those stars, might it see similarly organized boundary features? That possibility takes the uniqueness of Voyager 2's data and suggests it might help interpret phenomena on interstellar or even galactic scales. The prospect of building a dedicated interstellar mission arises frequently in these discussions. The knowledge gleaned from resurrecting Voyager 2's camera for an imaging campaign might inform how a future probe should be designed. Planners could equip it with modern sensors optimized for ultra-low light imaging, more robust cosmic ray shielding, or advanced software for real-time denoising. It could systematically chart the boundary from multiple angles, capturing not just particle flow data, but also high-resolution images of how dust, magnetism, and plasma waves shape the star's final frontier. From the standpoint of cosmic ray science, the patterns discovered, if they turn out to be wave-driven or magnetically shaped, might also explain certain anisotropies in cosmic ray flux seen near Earth. If cosmic rays travel along these filaments or spokes, that could localize or modulate their arrival paths. Studying that effect may help in modeling space weather or in developing better debris shielding for future crewed missions to the Moon or Mars. Such links show how even vague images of the distant heliopause connect concretely to safer human exploration.